So the second order difference equation that we have is yt minus 0.8 yt minus 1 plus 0.1 yt minus 2. And what is the first step that we should do to find the roots? I'll give you a hint. Says loads about your character.
Characteristic equation.
Close. Characteristic polynomial. So the very first step is to write the characteristic polynomial. And to do that, we are going to move those to the other side, and we have to rewrite it in terms of the lag operator. So yt minus 0.8 L multiplied by yt minus 0.1 L squared multiplied by yt. L squared when applied to yt would give you y sub t minus 2. We have y sub t in common. So we'll end up getting 1 minus 0.8 L minus 0.1 L squared. And I mentioned that if we want to write it as a characteristic polynomial, we don't want to write it in terms of the lag operator. We'd rather call it, a letter. Typically, it is said you could also use S. Standard notation is Phi of Psi, uppercase Phi. Later on, we will see Psi. Phi would be on the left-hand side, and Psi would be on the right-hand side. But both of them are polynomials. So that would reduce to 1 minus 0.8z minus 0.1 z squared. Our objective is to set that equal to 0 and solve for z. We don't have to go through the entire process because we had a derivation for this. We did it last time, and you can give me the formula. We'll just use the formula. You can correct me if I'm wrong. Yes, no. Am I missing this one? I think so. From last time.
Is it a positive B1?
Yes. The rest is correct.
And then in the root, it's also B1. But the square is 1, right?
T1 squared.
It's like B1 squared.
3G squared. B squared minus 4AC.
That plus or minus b, isn't it b, negative b plus or minus b squared?
So B squared minus 4AC. This should be 1, and that should be 2.
And should the bottom would also be 2?
And the bottom would also be 2, yes. So, yes,
Where did you get the 4 from? Nothing.
Quadratic formula from last time. So this is our derivation, so that's the first root. The second root would be phi1 minus square root of phi1 squared plus 4 phi2 divided by negative 2 phi2. Plug in the values of phi1 and phi2, so you've got to tell me what phi1 and phi2 are. So phi1 is 0.8, phi2 is 0.1, you plug it in there. Z1 is
Negative 9.099.
9.499.
Yeah.
And Z2,
1.099.
good, we have real roots, so not a big deal. Now we will talk about, the properties of these roots and see if the model is going to be stable or not. That will come later on. So we found the roots of the characteristic polynomial, great. And if we want to write phi of z in a factored form, if you recall, the factored form of phi of z is 1 minus lambda 1 z multiplied by 1 minus lambda 2 z. Yes. So what is lambda 1?
Negative 9.099.
No.
9.
I mean, what would make a factor 0? You can look at your notes. What is the relationship between Z1, the first root, and lambda 1? Relationship between Z2 and the second root, lambda 2, from last time. So Z1 would be 1 over lambda 1. This would imply lambda 1 is 1 over Z1, and lambda 2 is 1 over Z2. So we would have 1 over negative 9.099, and lambda 2 would be 1 over 1.099. What do we get? Negative 0.13. No, 1.8. Can't be 1.8.
1.099.
1 over. And how about that 1.9? 9.
Yeah, 0.09. 0.9099.
909. Last time I mentioned, sure, this is okay, but there is an easier way to find the roots or the lambdas, especially when we get to higher order models. So it is easy to do it here because it is a quadratic model. But what if you had a cubic equation or a fourth degree polynomial?
You guess.
You guess?
Good
luck with that.
I mean, I don't think you get it right, but you guess something.
That is true. So what would be the approach? I said there is an alternate approach which would make things easier.
Eigenvalue method.
The eigenvalue method. So I'm using F because that's what the book uses. So we know phi1, we know phi2. We want to find the eigenvalues. Phi1 is 0.8.
Yes.
Phi2 is 0.1 and 1 and 0. That's our matrix. Great. If you took matrix algebra, okay, linear algebra,
Online.
okay, you say you took it. How hard is it to find the eigenvalues?
I'm going to die.
Okay. So, exactly. So, sure, you can do this manually, but you can put this in the calculator and get the answer right away. And that's what I'm going to show. If you look in the calculator, you can press the mode button, and right now we have only real values, right? So I mentioned that it is possible for us to get complex numbers as roots for an equation. So if you don't change the mode, it's going to give you an error. So currently the mode is real. I'm going to switch it over to A plus BI. So here is the question, what is the next one? Yes.
Minus 7 degrees, should I change it back to radians?
It has to be in radian,
Okay.
yes. So normal flow radian, you can forget about it on this real and switch it over to A plus BI. That's great and all, but what is that part?
What do you?
That's. Oh, this is imaginary too. Remember last time I wrote an imaginary number as r multiplied by e raised I theta. And then I wrote it as r cosine theta plus I r sine theta. That's what that is. Hopefully this works. Let's take the square root of -1 to make sure it works. It does. Isn't it great? So if you have it in real mode and if you did square root of -1, you will get error. So make sure you set it in complex mode, because sometimes the roots of the polynomial will end up being complex, and if you don't set it in complex mode, when you find eigenvalues, it's going to give you an error. Okay, so now we have to enter the matrix.
Wait, how do you get that?
Second, X in this. I did go over this. Matrices, right?
Yeah.
Go to edit, select number 1. We have to specify the dimensions of the matrix. So we have 2 rows and 2 columns. So 2, 2. And the first value is P1, that is 0.8. The other is P2, 0.1. 1. Next one is 0. Good. And the second mode to exit has to be an option. Doesn't have eigen. So TR-84 doesn't have eigen. Thought it did, but it doesn't. So I'm going to use R. On an exam, I will give you the eigenvalues, or I will try to find,
A simple enough one we can do ourselves.
you can, but if you find the program, you can let me know. So So that is our matrix. So we're going to type I in A. And those are the values that I get. So you can see in the first row over there it says eigenvalues 0.9099 and negative 0.1099. And those are the values we have. You've got to keep in mind that this or these two values are for lambda, not z. So how do you find
Also, that second was not supposed to be negative,
what?
0.9099.
Oh yeah, thank you. So these two values, if you invert them, you will get z1 and z2. Does that make sense? So you can get, for higher degree polynomials, you can get it directly by getting the eigenvalues using your calculator, but calculator can't do it, so we will make use of R. Does that sound good? So this is what we did so far. We have a second order equation. And this part right here, 1 minus lambda 1 z, multiplied by 1 minus lambda 2 z, is simply the factored version of phi of z, the uppercase phi of z. I'm stressing this because later on we will do a psi, and psi will be on the other side. Now, I am about to try and find psi. So what I'll do is divide both sides by this term, the factored version. Good. We know how to find lambda 1. We know how to find lambda 2. We've done it already. So we can clearly come up with numerical values over here. Now, what we want to do is to decompose this fraction 1 over 1 minus lambda 1 z multiplied by 1 minus lambda 2 z as a sum. So I have this fraction and I want to decompose it and write it as a sum. And you may ask me why. If you look in the denominator, we have 1 minus lambda 1 multiplied by z. If you think of, if you recall the first order difference equation, when we had something 1 over 1 minus lambda 1 z, I wrote this as a series, an infinite series, because this is simply the infinite sum of a geometric series. Yes. So if I break this apart and wrote it as two separate fractions, then I will come up with two different series. Do you agree? and then I can manipulate them in some way. So here is a question to you: how do I break them apart efficiently? Give you a hint, how to. Partial fraction. So we want to split that up using partial fractions. So distinct roots. So we would have 1 over. How does it work?
Honestly, can't tell you off the top of my head.
What's the process? 2 distinct roots, 2 factors. How do we split it up? Partial fractions in part 2. Differential equations, Laplace transform.
Like years ago.
I'm in top 2 now, so we're not very
We have to 20.
You take some constant a and divide by 1 minus lambda 1 z plus some constant b divided by 1 minus lambda 2. So I have this function, and I'm going to split it up as a sum. I'm going to decompose it as a sum. The only thing preventing us from preventing us from decomposing it properly is we do not know the value of a and b, and we've got to find the value of a and b. If I cross multiply, in other words, I multiply by the denominator on both sides, I would have 1 equal to 1 minus lambda 1 z multiplied by 1 minus lambda 2 z, a divided by 1 minus lambda 1 z, plus 1 minus lambda 1 z multiplied by 1 minus lambda 2 z, b divided by 1 minus lambda 2 z. Yes?
Well, I have to rewrite this right
I've got some terms that are in common, so I could get rid of them. So those 2 will go away, those 2, oops. Got too excited there. Those 2 will go away. So we will have 1 is equal to 1 minus lambda 2 z multiplied by a plus 1 minus lambda 1 z multiplied by b. So the principle of partial fractions simply solves for a and b by first setting this to 0, solving for a, then setting that to 0, solving for b, and vice versa. I can get a 0 here if z is equal to 1 over lambda 2. Do you agree? So if z is equal to 1 over lambda 2, I have 1 minus lambda 2 multiplied by 1 over lambda 2, which will give us 1 minus 1. 1 minus 1 is 0. So 1 would be equal to 0 plus 1 minus lambda 1. Z is 1 over lambda 2. So times 1 over lambda 2 multiplied by b. Yes? Which would give us 1 minus lambda 1 over lambda 2 multiplied by 3. So common denominator, I can write it as lambda 2 over lambda 2 minus lambda 1 over lambda 2 multiplied by b. If I combine the numerators, I'll have lambda 2 minus lambda 1 divided by lambda 2 multiplied by b. Cross multiply again. For b would simply be equal to lambda 2 divided by lambda 2 minus lambda 1. Do we agree? This goes up there, that comes down here. Yes. Which I'm going to write it as negative lambda 2 over lambda 1 minus lambda 2. I'm pulling the negative out from the denominator. So lambda 2 minus lambda 1 will become lambda 1 minus lambda 2. Negative goes on top. Good. We have successfully found b. I wanted to find a using a similar process. So to find a, we're going to set z is equal to 1 over lambda 1. So 1 would be equal to 1 minus lambda 2 over lambda 1. A 1 minus, well, that term's going to become 0. Z is 1 over lambda 1 over lambda 1, 1 minus 1, 0. That's going to go away. Same trick, common denominator, which will give us lambda 1 minus lambda 2 over lambda 1a equals 1, which would imply a is equal to lambda 1 over lambda 1 minus lambda 2. Do we agree? Okay. So what did we do? Did a whole lot of stuff. So we found the value of a and b. I can keep it as a and b, but I'm going to do something so a and b might be too much, might make the equation messy. So I'll just call this as C1. C1 is a, and that would be lambda 1 over lambda 1 minus lambda 2. C2 is b, negative lambda 2 over lambda 1 minus lambda 2. Good. So that's what we had. That decomposes as C1, which is A, divided by 1 minus lambda 1 z. Yes. Plus B is negative lambda 2 divided by lambda 1 minus lambda 2. I'm calling that entire thing as C2. So C2 divided by 1 minus lambda 2 z. Good. Put myself up. Recall, it all started here. Phi of z, yt equals wt. Do you agree? That is the very first step. That was the characteristic polynomial. I took the characteristic polynomial, I factored the characteristic polynomial, I ended up, theoretically, these are the factors. And then I divided phi of z, and I ended up getting 1 over phi of z, w sub t. Yeah. That simply is that. Correct. This and that's are one and the same. Before we get to that step, I'm going to call that as psi of z. 1 over phi of z is psi of z.
You said that's the same as.
This is that. Okay. So I know that, or we know that we have decomposed 1 over phi of z like that. Do you agree? So I'm going to rewrite that part as c1 over 1 minus lambda 1 z plus c2 over 1 minus lambda 2 z. Sure, this is the problem, yeah. Geometric series. We use this with the first order difference equation. We are going to do the same thing because we realize that this part is 1 over 1 minus lambda 1 multiplied by z. So instead of a, I have lambda 1 z. Do you agree? But as a polynomial, we wrote z. But in reality, what was it at the beginning? L. It was L at the beginning. So there is a reason why I'm doing this. So the first one, 1 over lambda L is the same, 1 over 1 minus lambda 1 L is the same as 1 over 1 minus A. So I can write that as a geometric series. So C1 multiplied by 1 plus lambda 1 L. A is lambda 1 L. So A squared will be lambda 1 squared L squared. A cubed will be lambda 1 cubed L cubed. Dot, dot, dot. Do you agree?
You repeat that.
A is lambda 1 L. Yes. 1 over 1 minus A, geometric series. 1 plus A squared plus A cubed and so on. So A is lambda 1 L. I could write it as 1 plus lambda 1 L plus lambda 1 squared L squared and so on. Plus C2, 1 plus lambda 2L plus lambda 2 squared L squared plus lambda 2 cubed L cubed. Dot, dot, dot. same thing, right? I didn't do anything, out of the ordinary. First case, A was lambda 1L, the second case, it was lambda 2L. But do keep in mind, there is a W sub T on the right hand side, yes? So I've got to throw that in. So multiply by W. Y sub T C1 plus C2, yes. C1 lambda 1L, C2 lambda 2L, correct. C1 lambda squared L squared, C2 lambda squared L squared. Take a guess as to what the next term will be.
So you want to have the cubed, L cubed.
Plus dot, and we have WC on the outside. Good. Going to pull the L out, and I'll have C1 lambda squared plus C2 lambda squared multiplied by L squared. C1 lambda cubed plus C2 lambda 2 cubed multiplied by L cubed. Sorry, I meant to say lambda 1 cubed. Good. Is if we go back and track everything, all of this right here is psi. Right? So I started with 1 over phi of z, decomposed version, phi of z in terms of the series, phi of z, C of z, sine of z, decomposed version, series version, simplified. All of these are psi, not p. So yt would be equal. I'm going to distribute that wt in. Good. So the first term would be c1 plus c2 multiplied by wt. Yes. The second term is C1 lambda 1 plus C2 lambda 2 multiplied by
L and WT.
L times WT, right? But what is L times WT? L is an operator. I want L to go away, but you can't just erase L. But I do know when L is multiplied with WT, something is going to happen to WT. Hint, L is a lag operator. Lag would mean behind.
It decreases those elections. Really,
It would become T minus 1. same as squared when applied to WT. WT minus 2, yes, plus C1 L1 lambda 1 cubed, C2 lambda 2 cubed, W3 T minus 3. Dot, 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 dot. Going to write the jth term, there is a reason why I'm going to go with the jth term. But of course, it is not going to stop there, it's going to keep on going up to infinity. You with me? Great. This is simply equal to psi 0 WT, psi 1 WT minus 1, psi 2 WT minus 2, psi 3 WT minus 3, dot dot dot, psi j WT minus j, dot dot dot. Good. Psi sub 0, C1 plus C2, psi sub 1, C1 lambda 1 plus C2 lambda 2, psi sub 2, C1 lambda squared plus C2 lambda, C2 times lambda 2 squared, psi sub 3, C1 lambda 1 cubed plus C2 lambda 2 cubed, and so on. Last time, all the time before, I said, everything in life today, what you are today, is simply a combination of random things that happen to you in life. Okay? So what you are this week, all of these are random components, right? They're all normally distributed. So whatever happened to you today and what you are today is simply a combination of these mixed up different levels. Whatever happened a week before, 2 weeks before, you put them in different ways, and that's what you end up getting, right? Here is a question. Whatever you are today will be most impacted by what are you? The day before, or earlier today, right? And then the day before, and then the day before that, and so on. But eventually there would come a point, J, at which, things might be not that correlated, right? You're not going to regress on something that happened to you, 100 weeks ago, right?
Don't underestimate me.
So, that's what we call a dynamic multiplier. So now do you see what the C function or the psi function is? So if I pulled out, so whatever I have here, psi 1 WT, psi 1 WT minus 1, all the way up to psi j WT minus j, is nothing but the psi function. Why would we call it as psi z? Because we have the lag operators, just like we had it with phi of z. I have the lag values, I rewrote it as z. Same thing I can do it here. So there's one thing called the dynamic multiplier. So if I replace t by t plus j, so the first one would become t plus j. T plus j minus 1. psi 1 t plus j minus 1, psi 2 t plus j minus 2, psi 3 t plus j minus 3, dot, psi j. What happens to t plus j minus j? W t. Oh,
Sorry.
good. So we will get back to this later on and relate it to the autocorrelation function. The book calls it as the dynamic multiplier, so I'm going to keep it as is. So what is that dynamic multiplier? You take the partial derivative of y sub t plus 1 with respect to wt. I'm going to take the derivative with respect to wt, so what would happen to that term? Well, I'm taking the derivative with respect to wt, so what would happen to that term?
We just be itself. Right,
I want to take the derivative with respect to wt. Is that wt? No, it's wt plus j. Right. So if you take the derivative of, t with respect to x, what's the answer? Zero. So that will go away, that will go away, that will go away, that will go away. So none of them are wt. But that one right there, derivative of wt with respect to wt is 1. So you have psi j, and everything else will be 0. So 0 plus 0 plus 0, dot, psi j plus 0, 0, 0, dot. So that would simply be equal to psi j.
Are there zeros up there, next to the dynamic multiplier?
That's
This,
Yeah.
it's a partial derivative. So it's a funky sign. Psi j is simply c1 lambda 1 raised j plus c2 lambda 2 raised j. So what does this tell us? This simply tells us if I model everything properly based on whatever happened to you in the past, which pretty much is a combination of random things. I'm asking this question: if I change whatever noise that's going to happen today by 1 unit, what would happen to you 2 days from today, 3 days from today, and so forth? How do we find that? Using that number or that expression. All I have to do is plug in the value of j. So what are the noise that you had today? How does it affect you tomorrow? I'll just plug in j. So 1, 1. I know the value of C1, I know the value of C2, I know lambda 1, I know lambda 2. I'll simply get a value and I'll say, this is what's going to happen tomorrow. And say you want to know about 2 days from today, you will change it to 2. And whatever happened, if I change that noise by a tiny bit, how do you know what would happen 2 days from today? 2, 2. 3 days from today, 3, 3. Now what would happen as time goes by? would this value become smaller and smaller and smaller? Or do we expect it to get larger and larger and larger? Larger? And think about what I said. It'll be smaller, right? Whatever you are today, you know, you can't look back 100 weeks, you know, whatever happened 100 weeks ago, then that would be kind of very, very small. Same thing, if you're going to look forward based on whatever you model today, perhaps it is going to be accurate for 1 day, 2 days, maybe 3 days, maybe 4, but 100? No, can't happen. Does that make sense? So the example that we did, we will continue with this concept on Thursday. You have questions, talk to me, or talk to you on Thursday.